I want to now to drive you through the second lemma. So we saw the lemma of the variational form that will help us for proving continuity of entropy. And now we're gonna see that a lemma about H being not too concave. Like it's a really important lemma, which is like if we let rho x with rho I believing to the small trace of A be a set of states, and we let the probability of x be a relative distribution. So you have a set of states and some probability distribution. Then you have the sum of x px of h px, which is inferior to h of the sum of x px of set of state px, which is inferior to the sum of x of px of h px plus h of creative exploration over article stuff. So the first inequality just concavity, but we're gonna all see all of this with an example. So imagine like you have Pokemons, and so you have 3 boxes of Pokemon. So you have a box 1, which is like Pikachu, for example. The second box is like Dracofer, and the third box is like a mix of both of them, like Pikachu and Dracofer. Okay, and so let's say like you have a tract, you want one of this box, and you have like 50% to have only Pikachu, 25% are having only Dracofer, and 25% to have Pikachu and Dracofer. And so yeah, it means like here, because you only have Pikachu, like you have pure states, like there is only pure, it's not mixed, there is only one stuff, so it means the incertitude of a pure state, the entropy of a pure state is 0. Same here, and here it's like 1, because like it's have Pikachu and Dragover, so you have a mix there, you have 2 of them, and so it's just like rho minus rho log rho, and so it's 1 over 2, log of 1 over 2, it's minus log over 2, but so it just gave 1 at the end by applying the formula of the entropy and on the logarithm. So this lemma our lemma that we wrote just tells us that so if we remember, our lemma was this, sum of x of p of x of h of px is inferior to h to the sum of x px of px inferior to sum of x px h of p of x plus h of px. And so this one just tells us that if someone chooses the box that has chosen by the D, the average entropy that will stay on the card is just the average of all the entropies of each box. So basically it just median entropy. Um, so it's just like 0.0 plus 0.0 plus 0. Multiplied by 1, so 0.25 bits. Because you see, like we calculated them like 0, 0, 1. Okay, and so basically you have this, and so that's the first one, and so for the second one, so if we call this like 1, if we call this 2, here if we take all the three it's like they tell us, oh, if we take all the cards of the three box and we like put them all into a big package, into a box 4, like, which is box 1 plus box 2 plus box 4, our uncertainty will increase, like, so just like we create a new box with all your new Pokemon cards, and so putting all of them together, you just have a new box with more uncertainties as before, because you don't know which one was the original box. So that's why it increases. And the third one is like, what is the maximum of uncertainty that we can add by mixing all of this, like we mix all of this into the equation too, but what's the maximum of uncertainty we could have added? And the answer is just no more than the uncertainty of the D itself, you run something, your random choice, like, and the stuff that the uncertainty of what you launched, like entropy of X. And so in our case, like, we have three choices with three faces, so the entropy is just 1.5 bits. So it's just like 3 multiplied by 0.5, which gives 0.5 bits. And so the maximum is just this plus this entropy of it, and so that's 0.25 plus 1/5, and so that gives 0.1, which gives us 1.751 bits. So yeah, so 1.5 just, the degree of it's just a minus the sum of its entropy of 4x, like 4x. So currents, like, minus 1/2 log of 1/2, 1/4 log plus 1/4 plus 1/4 log 1/4, and so 3 of this is like minus 0.5, and with the minus at the beginning it just gives us plus 1 minus 5. So yeah, that's the maximum we can have as an uncertainty. So yeah, like, mix the state that's in the box too, like create disorder, but like that's our question too, but this disorder explanatory is like strictly limited by the classical information that allowed us to mix this mixed stuff, to mix everything. So let's go through the proof of this lemma. For doing it, we are going to use an auxiliary x that will keep in memory the results. So we define a classical quantum state that will allow to do this. So of x of px of x 0 or x. Now this x is considered a memory and our x like is an A and is a quantum state where we want to compare the entropy. And so first what we want to prove is like why this entropy is like equal to the sum of like why it's equal to the entropy of x plus the sum of x px of h of px. And yeah, so basically we just want to prove that have this. The first time. So basically what we have is like if we check the orthogonal basis as x are orthogonal sets, we have a diagonal matrix by block, which means like have row 1, positive 2, row 2, etc. And if we take those logarithms about it, just log of rho xa of log p1 rho 1 log of p2 rho 2, etc. And so thanks to the for the property of the logarithm, we know like the log of probability of x x just like the log of probability of x multiplied by ai plus the log of px. And so if we calculate the minus the trace of this, our diagonal like separate between two terms, so one linked to the classical probability will give us like so if we take like it will give us like our entropy of our system h of pxx, which we can call h of x, the sum of x of px h of px, which is the quantum one. So yeah, as we integrate the classical variable into density matrix into the form of block diagonals, the global entropy just the entropy of the classical choice plus the average of the entropy of the quantum blocks. So yeah, let's go through the steps knowing that. So the first step that we need to write is that we have h of ax is just equal to h of xa minus h of x, because you know you have a, you have x, so h of ax for xi minus x is just h of a knowing x. And so, yeah, we have this. And if we replace this by the value we find for xa into the point 1, it just at the end h of x now here, or if you prefer to write it correctly, it's like h of pxx plus the sum of x px h of px minus h of x. So yeah, we can see like a minus h of yeah. So yeah, how to want to be correct about it, we can write h of a px x. Well, we can like, I think it's okay like to write x directly, so it will be easier for us. And after we do change of variables that we did here, so have this. So just the sum of x of px, h of px, h for x. So it means that if we know the variable, the classical variable x, the uncertainties that stay into a, just the average of the incertitude of each state's rho x. But we know also that conditioning can only reduce entropy, because you have your two system, and so it just means like with like h of a when x is inferior to h of a, because you just know something more, so even certainty just reduce itself. And so the reduced state rho a can be obtained by taking the partial trace for x. So we have rho a of trace of x for xa, which is equal to the sum of x of px rho x and yeah, because trace out x and x is just this, so yeah, but a is here, so consider sum of x of rho x. And so the entropy of the system, it just means that it's like h of a just h of this, the same of x of px rho x. And so by replacing HA knowing x and HA into our inequality, we get so we have this inequality, h of a makes x equal to h of a, as I explained, and so replacing them, we have like h of a being h of the sum of x for x or x, and h of a and x being the sum of x of px h of rho x. And so we just proved like the first part of the lemma, the concativity one. So yeah, this one. So now we want need to prove this one. So yeah, as we see, like the first inequality is just concavity, and so the second one is so yeah. But anyways, that's what I told you with the Dracoffer stuff, etc. And just like you mix all in the bag like a tray box, like a box for us. The uncertainty of all the box, so it will be like the mix of all of them um, will be separately like than just the sum of each one individually. So at least so it's just the definition of concavity, whereas the mixture, like if you take a function about something, it will be just superior about the mixing of the f. Like if you take f of the mix, it will be superior to the mix of the f. F of the mix is superior to the mix of the f. So yeah, basically we have this, and so for the second step, um, we just want like to have the superiority burn. So yeah, that's what I told you just 1 minute before. So we just want now the second part just to try to have now h of the sum of x of bx for x inferior to sum of x of variety of x of h bx plus h of bxx, where I called it hx in my stuff. So yeah, let's try to do it. We just need to keep in mind that h of xa is inferior to h of x plus h of a, like the answer, like it's just subadditivity of von Neumann, which is like if you have a system A and a system B, then yeah, h of x plus h of a is equal to h of xa. So if we replace this by their expression, like we just signed before, that h of xa is just h of x plus the sum of x of bx h of x inferior to h of x plus h of the sum of x or x for x bx for x. So you know h of xa is just like h of ax is h of x, and so h of ax is just the sum of x of bx of h bx plus hx. So that's why we would have about this. And so if we isolate HA, which is the entropy of the mixture, um, H of the sum of x by x by x, um, And so to obtain our circular bond, we just need to have HA is equal to H of XA minus H of XA, or more simply like so, H of XA being equal to maybe H of XA being equal to maybe we can use this formula instead, like we wrote H of A minus X just H of XA minus S of H as we saw earlier, and so it just H of XA being equal to H of X plus H of A minus X, and so it just equal to H of X plus the sum of X of Px H of Px, and so because H of A is inferior to H of XA, we can write like uh, we can write like H of A is inferior to H of XA, which is represented by this, so which is equal to H of X the sum of X of Px H of Px, and so we basically have H of A being inferior to the sum of H of X plus the sum of X of Px of H of Px. And so by replacing with the original notation, we just have H of the sum of X of Px, which is inferior to the sum of X like plus equal to H of Px. So you see there's a beginning with a variable change plus the sum of X of Px H of Px, and so we proved our second inequality. And so basically it just means also that what we've done here was not was was not really useful here. Like we could have begun to say H of Ax is equal to this, and so H of x is just this plus this. So just this plus this that we calculated before, and so because H of A is equal to H of xa, so we just this, and so we find this, and we replace by our notation. We found literally what we want. So yeah, basically that's it. And so if we calculate all of this, like we would have seen like with your Pokemon cards, as a super like here it's 0. This. Now here, if we like take our formula at the beginning, as we wanted to prove, we would have proved that like here, like we would have 0. So here's 1.75 now. Here's like 0.25 as we write, and here it would have now like 0.94554 bits. So that's the minimal uncertainty, the minimum entropy, real entropy, and the maximum theoretical entropy. which is just the entropy of the states plus all the entropy of the D here. Um, so yeah, that's it. Thanks for listening.